Things are looking good for Miami.
Pretty much had no downtime because we were all going to the week. We literally just went over there, grabbed some water, had like a 2-minute talk, and we were like, oh, so good. So good. Parents were like right in front of us.
Yeah, it was like
Use it, or you had it.
We lost. I know we used to get
Okay, I want us to finish up notes from Friday. So Friday we talked about second derivative and curvature, right? So concave up looks like a parabola opening up, concave down, parabola opening down. Point of inflection is that transition point from one concavity to the next. And we went through concavity sine line, second derivative sine line, but same process as first derivative test, right? Very much the same, except everything that we do is from the second derivative function. We find the critical points from there, we set equal to 0, we plot them onto our sine line, we test the intervals. Change in sign means there's a point of inflection. Positive is concave up, negative is concave down, right? So once you have the sine line in front of us, it's pretty straightforward. All right, now the back page is something called the second derivative test, and this process is not called the second derivative test. This, I'm calling it the concavity test. I don't think there's an official name for this, but the second derivative test is something else. Okay, so let's talk about that. That's on the back. So the second derivative test finds relative max and relative min. Okay. Does not find the point of inflection. So it actually does the same thing as the first derivative test, but just through a different method. Okay, achieves the same as first derivative test. Both the first and the second derivative tests are trying to find max and mins of the graph. Okay, so these are the steps, but I think it's easier if I just draw a diagram and work from kind of explain it from that perspective. So let me draw an example here. Let me draw a graph. Let's say we have a parabola here. Okay. So here's our function. Let's say the function has an order pair of 1, -2. All right, so we're basing off the graph first. F prime of 1, what would you say F prime of 1 is? 0, slope 0, right? F double prime of 1 is talking about concavity. So this point is part of a what? Concave up or concave down? Concave up. So concave up is going to connect with positive or negative value for the second derivative. Positive. Okay. So we know this is true, right? Order pair, slope 0, concave up. And if I have concave up and slope 0, if I can pair these information together, that's going to restrict the point to be this point. And this point must be a what? A relative minimum. Yeah. So that's what we're able to achieve with second derivative test. Basically, if we didn't have the graph in front of us, and if we know these two are true, if we know our slope is 0 and our graph is concave up, then those two information paired together is enough for us to conclude there must be a relative minimum. Okay, so let me include that information as well. Slope 0 and concave up. Means relative minimum at x equals 1. Okay, let me, any questions there? Let me draw the other scenario. Or
Wait, yeah, I do have a question.
Yes, go ahead.
How is second derivative of 1, how is that greater than 0?
Okay, because if you look at this graph here, if a point is part of a concave up graph, it's going to have a positive concavity. So it could be like 3, it could be 5, it could be 6. We don't really, the value is not that important. What's important is the fact that it's positive, right? So Friday, we discovered that if I get a positive value for my second derivative, that's going to translate to concave up.
Oh, okay, I gotta know.
And so right now we're looking at a specific point. The specific point is telling us a positive value. So that's how we know that it's concave up.
All right, thank you.
Okay, good. Let me draw the other scenario here. So for this graph, let's say f of -1 is 3. What would you say f prime of -1 is? Also 0, right? 0. And then f double prime of -1, second derivative. This is part of a concave, what? Down, which means that it's going to translate to a positive or negative value. Negative. So if I can pair the information of slope being 0, and I know it's giving me information that it's indicating that it's concave down, then putting those two pieces together, it's going to restrict that point to, we can conclude that point must be a what? Relative max. So this number could be like 5, it could be 8, it could be 1/2, right? This number here could be -5, -6, -8, okay? But the important thing is we don't really care about the number, we just want to know that it's positive versus negative. So this is what we're going to be able to do. We're going to gather information about the slope of a graph, and then we're going to move to the second derivative function. We're going to gather information about whether it's concave up or concave down. And then just by looking at these two pieces of information, we can conclude that it's relative minimum without looking at the graph. Okay. Let me highlight where we run into some issues here. I think we run into some issues because of the fact that if we don't verbalize concave up, and if we can't visualize the graph in front of you, I've seen where we struggle with this. Because if you're just looking at the fact that if you're just staring at a positive value, I think it's easy to connect positive with maximum and negative with minimum, right? It just feels more natural. But in this case, positive is going to be minimum, right? And I think that's a hard jump to make unless you do some additional steps. If you can verbalize second derivative positive value as concave up, and then draw a picture of concave up, you know that there's no relative maximum in sight, right? The only thing that is connected is that relative minimum. Okay, likewise over here, if you see a negative value for concavity, and if you don't make any additional connections, I think it's tough to match these together. I think we want to associate negative with minimum and positive with maximum, but that's not the case. Okay, so negative concavity is going to connect with maximum. And to bridge that gap, I think it's helpful if you can say to yourself, negative concavity means concave down. Concave down looks like this. And so the only relative extrema that I see is a relative maximum. Okay, so I was going to let you know ahead of time, this is what we're going to struggle with. Mixing these up is easy. Okay. Okay. We're going to go through example 2, but let me go through the steps using my summary sheet, and then we can go through example 2. So my summary sheet here, the purpose of the second derivative test is to use f double prime, use the second derivative function to find the max and mins of the graph. So the steps that we take, we're still going to find f prime, we're still going to see 0, we're still going to find critical points. So your initial step is going to feel like the first derivative test. Okay, you're still gathering the same information that you are gathering from the first derivative test. But rather than creating a sign line, we're going to go through a different path. We're going to find the second derivative function, and we're going to plug these critical points into the second derivative function. So let's say we have a critical point from f prime. From here, we can plug into the second derivative function and see if that gives us a positive or negative value. If it gives us a positive value, we know a second derivative positive value means concave up. If it's concave up, it's going to look like this. If it's going to look like this, it must be a relative minimum. Okay. Let's say we had another critical point, and we evaluate that second critical point into the second derivative function, and we get a negative number. A negative second derivative value is going to mean that it's concave down. If it's concave down, the graph looks like this, and that's going to be a relative max. So again, I mean, I think the graph helps so much, just to be able to visualize the graph, because sometimes, even if you're looking at up, if you don't have the graph in front of you, sometimes it may be easy to get these mixed up, right? You want to think of up as maximum and down as minimum, but if you have the picture in front of you, I think it's going to make that connection a lot easier to, so that you're not getting thrown off. Okay. So let's look at example 2, and all the steps are highlighted here. It's just I have a kind of drawn out a little bit more. Okay. So we're going to find the relative max and relative min, okay, using the second derivative test. So we're still going to find f prime. Okay, so we can go through power rule, and what do we get here? What's our derivative?
3x.
Mm-hmm.
3x squared minus 8x minus 3.
Good. Okay, we're still going to set f prime equal to 0. We're still going to find critical points. So your initial step is going to feel just like your first derivative test, because we're achieving the same thing. Okay, we want to find max and mins, and that's going to come from f prime. Oops, 0. We solve for x, and what do we get? Oh, critical points. Mm-hmm. Now, if we want to go through first derivative test, we would create our slope sine line, right? And then see if there's a positive or negative sign, and seeing if there's a max or min that way. So that's first derivative test. Okay, but we're going to practice with the other methods, so this is not the path we're going to go down, even though it would achieve the same thing. Okay. But instead, we're going to test these critical points using the second derivative function. Okay. Rather than a sine line, looking at the signs between these critical points, we're going to plug it into the second derivative function. Okay, so that means we have to find f double prime first. Okay, so what will that be? Good, 6x minus 8. Okay, so I want us to be careful with this step as well, because we're not going to set the second derivative function equal to 0. Right? If we do, that's something else, right? If we do that, then we're gathering information about concavity, and that's something else, right? So we got to be careful. It's easy to mix all these things together, but we're using the second derivative function specifically to help gain information about these critical points from f prime. Sorry, I lost my page here. So we're not going to set this equal to 0. We're going to use the second derivative function to test these points specifically. Okay, let's test 3 first. Okay, what do we get? Multiply, right? Yeah, 18 minus 8 is 10. The 10, that number is not that important, right? What's important is the fact that it's what?
Positive.
Positive. Okay, so let's make the connection here. Positive means what? Good. Concave up. Let's draw a picture to help us visualize what concave up looks like. And we know that the point that we just found has a slope 0, so we must be staring at a point. So there must be a relative minimum, yeah. So again, it's a tough jump if you're just looking at that 10 and then trying to conclude that it's a minimum. But if you can connect the fact that the 10 is concave up looks like this, it's a lot easier to convince yourself it's relative min. Otherwise, if you're just looking at that 10 and you're thinking positive, you're going to say maximum, right? It's easy to get these mixed up. Okay, does that make sense? Okay, you guys want to try negative 1/3 and see if you can make the correct conclusion for what's happening at negative 1/3? So you can follow the steps that I did, but just do it with negative 1/3. Okay, try that. So we confirmed that there's a minimum at 3. Let's see what conclusion we can make for negative 1/3. Okay, what you guys find here? Negative 10. Therefore, there's a relative max. Okay, so let's make the connection here. Concave down. Concave down looks like this. The only place with the slope 0 for concave down is that point, and that point must be a relative maximum. All right, any questions with this? Yes?
How do you know that the slope is 0? Is that because we set the first derivative?
That's right, yeah. We set the first derivative equal to 0, so we know that these points are confirmed slope zeros. And then from there, we just want to know, are the slope 0 going to be part of concave up or concave down? And that's what the second derivative can kind of help narrow down. Oh, and then to that point, I do want to add something to that. It's the fact that what happens if we get a second derivative equal to 0, right? What if we don't get a positive or a negative value? If we don't get a positive or negative value, then we don't know whether it's concave up or concave down. It's inconclusive. So this test, okay, so there's two things, right? Compared to the first derivative test, it's more convoluted, and it's not as, it doesn't work as well as the first derivative test, right? Because if the test is inconclusive, then the only way to find max and mins is to go back to the first derivative test. So the question is, why don't we just stick with the first derivative test if the second derivative test is not going to be as good and it's messier to use? So the answer to that question, AP exam produces questions sometimes that requires knowledge of the second derivative test. And if it asks the questions in a way that even with first derivative tests, you're not going to be able to conclude to the correct answer. Okay, so I want to show you an example of a problem that I've seen on the AP exam where if you didn't have knowledge of the second derivative test, you're not going to be able to know whether we're dealing with a relative max or relative min. So this example won't take a lot of space. If you guys just include it at the bottom of the page. Let's say our function is continuous, differentiable, which means that it's continuous. So let's say it's a smooth curve. And the only thing that's provided for us are these three things. F of 3 equals 2. F prime of 3 is equal to 0. And F double prime of 3 is equal to 1/5. So based off of this information, we want to know what conclusion can we draw about this point. So, okay, let's see if we can interpret what these functions and derivatives are giving us. 3, 2, that's just the order pair. That's just the physical point on the graph. Okay, what does F prime of 3 equals 0 tell us about the graph?
Slope is 0.
Slope 0. But even with slope 0, we don't know what's happening, right? We know it could be this, it could be this, but then it also could be neither, right? It could be neither max nor min. So slope 0 is still not enough to help us gain enough information about whether there's a relative max, relative min. So we're going to go to this third statement. Okay, what does that 1/5 tell us? Wait, 1/5 is positive, right? So positive is concave up. Okay, so we know slope 0, we know concave up. Let's draw a picture of this graph to help us make the correct conclusion here. So order pair 3, 2. I know through that point I want a slope 0, so I'm going to put a dotted line to indicate that's the horizontal tangent. But I have to force a concave up through this graph, right? So the only way I can draw a concave up is if it looks like this. So the only way to draw the graph is this way. So if I can draw this graph, it's a lot easier now, right? This must be a relative what? Minimum. So imagine if you're trying to do the first derivative test using this information, you know your slope is, you know your critical point is at 3, but you don't know what f prime of 2 is, you don't know what f prime of 4 is, so you're kind of stuck, right? First derivative test is not going to be sufficient because you don't have enough information. So this problem kind of forces us into a second derivative test knowledge. Okay, any questions? Okay, let's go to our quiz review. Hopefully you guys printed it out. If you didn't, you can kind of just copy the problem down and we can go from there. So for each of these problems, I'm going to kind of recap, highlight the steps, and then have you guys try it. Okay. So number 1, it says find critical values. So how do we find critical values?
Set odd derivative equal to 0.
Yeah, f prime equal to 0. And solve for x, and that's it. Okay. So critical values is kind of like the first step of other problems, right? EVT is the first step. First derivative test is the first step. But here, we're just finding critical values. No need to test, no need to compare with intervals. But I do want to highlight a couple of things here. We're dealing with a polynomial, so we don't have to worry about the denominator. But what if there was a denominator? How would you find critical points that way?
Set the denominator equal to 0.
As well as the numerator. Okay, so we got to look at both locations. Okay, in this case, it's not going to be an issue, just the numerator, but just want to make sure I include that statement. So we're going to make sure we set the numerator equal to 0, but we also are going to set the denominator equal to 0. So here we're looking for slope 0, but we're also looking for slope undefined. Sharp turns, critical, vertical asymptotes, holes, we want all of it. Okay, so critical numbers are going to be numerator and denominator of f prime equal to 0. And then solve for x. Okay, all right, so try that. See if you can practice going through those steps. And then we can talk about what you guys got. So find the derivative using power rule. Set the derivative equal to 0. Take out a GCF. Solve for x. We should have come across 2 critical points. Okay, what you guys find? Say it again. Close. 5/3. Okay, yeah. So just have to get those fractions flipped around. But yeah, you had the right idea. So here's our first derivative, set equal to 0. There's a GCF that we can pull from each of these terms. Continue factoring the trinomial, 5/3 of 1. Oh, okay, yeah, there's a bell for lunch, for the B lunch students to go down to the cafeteria.
Like, when people are out,
They don't know when to come in, right? Yeah, they started this week. Any questions with? Okay, let's look at number 2. Find the absolute extrema. Okay, so this is extreme value theorem. Let me remind the steps. Remind us, go through a recap of the steps, and have you guys try number 2. So extreme value theorem. The purpose of extreme value theorem is to find the highest and lowest points on the graph. So we have one condition to make sure it passes. It needs to be continuous on the closed interval. If we're doing the polynomial, there's no worries about it. You can just make the statement without doing any additional checks. But what if there's a rational function? Then what do we have to do to take care of the fact that the condition may not pass every time? Good. Denominator equal to 0. We have to look for vertical asymptote. We got to look for holes, right? Doesn't mean that if you find it, doesn't mean that you can automatically say that our function is not continuous on closed interval. You got to compare it with the interval, right? So just want to make sure that we remember those steps. All right, and then after we confirm it's continuous, which it will be for our problem because we're dealing with a polynomial, we can go and find critical points. So just like how we did with number 1, right? You set the derivative equal to 0, you solve for x. If there was a denominator, you would set that equal to 0 as well. But are we going to just blindly use any critical point that we come across? What do we have to confirm? Yeah, interval. Go back and double check your interval. It's possible you find all these critical points and none of them are valid, right? We have to make sure that they fall inside the interval. So the very least is no critical points, and you only test the endpoints. You only test 2 points. But if you have critical points that fall inside the interval, then you're going to test critical points and endpoints back into the original function, and then you're going to compare the y values. Okay, highest y value is your absolute max, lowest y value is your absolute min, and the emphasis is on the y value. Okay. If you just give me the y value with no x's, that's fine. You'll get full credit. If you want to de-emphasize the x value in parentheses, that's fine as well. But if you give me ordered pair, then I'm not so sure that you understand the emphasis on the y value. Then you will lose, you will not get full credit there. Okay, so either the y value or the y value with additional information for x, but not ordered pair. Okay. All right, any questions with extreme value theorem? All right, can you guys try number 2? So find f prime, set f prime equal to 0. Okay, we should have come across two critical points. What'd you guys find? Negative 1 and 2. Okay, are we going to keep both of them?
Yeah.
Yes. Okay, they both fall inside the interval. It checks out. So we have 4 points to test, right? 2 endpoints and 2 critical points. And they all go back into the original function. Use your calculator, find those y values, and then compare those y values. Okay, we should have found these y values here. Negative 19 is its lowest y value, so that must be the absolute minimum. 8 is the largest y value, so that must be the absolute maximum. Emphasize the y value, de-emphasize the x value. And I'm looking for your condition as well. Make sure you're also writing at the beginning of the problem, continuous on the closed interval. Right, so that requires a full credit as well. All right, any questions with 2? All right. Give you guys a minute here. Okay, before we move on to number 3, let me highlight the steps and kind of recap what Rolle's theorem is. So Rolle's theorem, the purpose of Rolle's theorem is to find the location where there's a slope 0. We're looking for slope 0 somewhere along this curve. Okay. And we have to first make sure, though, that our conditions are in place, meaning that we have to make sure that there's no issues in our interval. So we have to make sure there are no breaks, there are no vertical asymptotes. If there's a denominator, we have to look for that, that vertical asymptote, make sure that it doesn't impact our interval. Now, 95% of the time, if it passes the first condition, it will also pass the second condition. So usually, you're not going to have to do anything additional with differentiable, unless it falls into 2 categories. If you're dealing with this a fifth root or third root or an odd root, then there's additional work that needs to be done. You got to set the denominator of the derivative equal to 0 and look to see where that sharp turn is located and seeing if it affects the interval. The other type is absolute value function. But this you can just graph. We're not going to see a whole lot of this, but I just want to just point out that 95% of the time, you're not going to deal with. You can if it passes the first condition, you can just go ahead and state that second condition without doing anything additional. Okay, because most of the graphs that we deal with are smooth curves. So it's really only this you got to worry about. But either case, if it passes both conditions, we know our graph is nice and smooth between our endpoints. So we still need something to confirm that there's a slope 0. So we have to test our endpoints. We have to plug our endpoint values into the function and confirm that they're actually level, that they actually have the same y value. If they have the same y value, we know we can draw a horizontal line between them. If we can draw a horizontal line between them, that means there must be a place where there's a slope 0. So we just set f prime equal to 0 and we solve for x. Okay, when we solve for x, we have a conclusion, we have an answer, and that answer is guaranteed to fall between our endpoints. If you have more than one solution, you got to make sure that they fall inside the interval. Okay, if it falls outside, we remove it. If it lands at the endpoint, we also remove it. Okay, we only want what's in between. Okay, so let's walk through number 3 here. All right, Rolle's theorem. We have to confirm our conditions are good to go. Are we looking at a polynomial here? Okay, not a polynomial, right? We're dealing with a rational function, which means that there may be some continuity issues we have to be aware of. Okay, what do you guys see? Yeah, and how would you find that?
Same denominator.
Okay, denominator is 0. So if there's a variable in the denominator, that's a red flag. That means we got to do some additional work before we jump into our problem. So if I solve for x, I get x equals 0. So what does this tell us about the graph? Okay, okay, good. But more specifically, what's happening there? Good. All right, vertical asymptote. You don't have to specify it on the quiz. If it's undefined, you can just make that. You can just show the work for it. Okay. Now, if there's a vertical asymptote, does it automatically negate our condition? Okay. We always have to go back and check against what? Interval. Okay. Interval. Is our problem landing inside our interval?
Yes.
Yes. So is our function continuous on the closed interval? Not continuous. So we stop the problem. Okay. If it's outside the interval, we move forward. If it's inside the interval, we stop because it fails and there's nothing more to do. So we say our function is not continuous. On the closed interval from -2 to 2, Rolle's theorem does not apply. Okay. So that's the end of the problem, but I want to just go through the steps, just talk about the steps, make sure if it does apply that we know what to do. So let's say it was continuous. Then you can just go ahead and state your function is also differentiable. So I'm gonna, okay, so let me put this here. So if problem applies. Sorry, if conditions apply. You can go ahead and state that second condition, which is our function is differentiable from -2 to 2 using parentheses. And then you would take the endpoints, plug into the function, and see if f of -2 produces the same y value as f of 2. And then if it does, then you know there must be slope 0, and you can set f prime equal to 0. Right. If we want to go through f prime, what method do we have to involve? But first to get to f prime though. Yeah, derivative. Quotient rule. Okay, quotient rule. Okay, good. And once we find quotient rule, once we find the derivative, there's a numerator and denominator portion. I'm looking for slope 0. So am I going to set both the numerator and denominator equal to 0?
No.
Just the numerator. Okay. So I don't just go through that because that can be confusing, right? If I ask you for critical values, you got to look in the numerator and denominator. But if I'm only looking for slope 0, because that's what Rolle's theorem is trying to guarantee, we're only looking at the numerator. Denominator is not going to give us slope 0. Okay, just want to point. I know it didn't apply for this problem, but at least I want to go through the full Rolle's theorem. So when we do another problem tomorrow, we'll know the steps.
Mr. Yang? She has a question.
Yes, sorry.
I was just wondering, sorry, I just blanked that. Oh, like when you have to explain it, you have to say like, because there's a vertical asymptote.
No, you're not saying. As you can do this to the side. You can just jump directly here. This is good enough.
Okay.
But I do want to kind of walk through the process so that you know how to look for those things. Right? Okay, let's look at number 4. But before we go to number 4, let me recap mean value theorem. Mean value theorem feels a lot like Rolle's theorem. First two conditions are the same: continuity, differentiability, but it's not as restrictive, right? We don't have to have a slope 0, so we can jump directly into our formula. Right? So our formula is find the endpoints, figure out the slope. Once you have the slope, you set it equal to the derivative function, and from there you can gather where that location is for that specific slope. And then again, just like with Rolle's theorem, whatever answer you get at the end, it has to fall inside the interval. Outside is removed. If it lands at the endpoint, it's also removed. We only keep what's in between. But you're guaranteed at least one solution in between your endpoint. Okay. All right, number 4. Mean value theorem. We want to test continuity. We're dealing with square root, so square root is not going to have any issues in terms of there are no sharp turns. The only thing you got to be worried about is, are the endpoints going to give us any negative values, right? We can't have negatives inside the square root, so we just plug 3 and 5 into the function and make sure that they don't give us any negative values. So 3 in for x, I get 25 minus 15. That's a positive number. We're okay. Plug 5 in for x, I get 25 minus 5 times 5, which is 25, which is 0. So square root of 0 is not a positive number, but it's still okay, right? Square root of 0 is still defined. So it looks like continuity is not an issue. We can say our function is continuous. Make sure you specify your closed interval. And if it's continuous, it's also differentiable, right? We're not going to have problems that has issues with sharp turns. Okay, but differentiable is with open parentheses, right? So we can move into working this formula here. All right, so how would you begin this process?
Finding the Y's.
Good. So we'll start with the 3 and 5, plug into the function, and then we're going to be working the right side of our formula. Okay. Some students in the previous period were asking, well, can we just do the derivative first? You could, but I would suggest against it, because if you find the derivative too soon, you may be tempted to plug the 3 and 5 into the derivative, and that is completely off. So I feel like if we can do our work on the right side, it'll hopefully limit the potential of making a mistake with the derivative. So let's find that number first, and then find the derivative, and then we can have a clear path, right? Derivative equal to the number, and then we just solve for x. Okay, so let's save the derivative for a little bit later. I realized from previous years, students finding derivative too soon led to issues. Okay, so we're going to focus our attention at the endpoint. Let me write the formula here. All right, so f of 3 so that's 25 minus 15, which is 10, negative 10 to the 1/2, which is negative square root of 10. F of 5. Five times 5 is 25. Square root of 0 is 0. Okay, I have my ordered pair. So what can we do with these numbers here? Yeah, find the slope, right? Find the slope to the endpoints. Change in y over change in x. Okay, careful with your negatives here. Okay, we have this number. Now we can find what? Derivative. Okay, so derivative, what's required here? Chain rule. Okay. All right, we'll finish this tomorrow. If you guys can cross off number 5, because we're going to need more room to finish number 4. So I want to do the rest of this problem with you tomorrow. But for homework, if you guys can do 5, 6, 7, and 8. I think those are more straightforward. You should be able to get through those hopefully easily. And then tomorrow we'll do more review. I have another review sheet for us. Wednesday review, Thursday quiz, open notes. And then Friday, for any of those who need to do or who want to do recovery for their related race test, the directions are on Teams. Assignment is due on Wednesday, but the test is on Friday.
Mr. Yang?
Yeah.
Did you say it was 6, 7, 8?
Yeah, number 6, 7, 8. Yeah.
Why?
It would get horrible. I want to do that.
Bro, I just found I've been holding on for
Well, if you want to put on the series, so.
Oh, I thought you said you watched it.
I did. I watched the beginning. It was like a dollar face. And I believe it was a free gap. At least you wanted before. This was like 6 months. Before his good surgery.
Good knee.
Foot surgery. And he put 4 nights, 6 hours a day. And so that is
I had like 64 last year.
Okay, if you're on Teams, you're free to go.